Moving on, q dash is nothing but the displacement matrix in your local coordinate, and we have found that that is equal to the transformation matrix into the displacement matrix in the global coordinate. Now we have the transformation matrix like this one. Now moving on, we should be finding out the direction cosines L and M. L is nothing but direction cosine in the x direction, and M is nothing but the direction cosine in the y direction. We will be considering element having node 1 and 2. The length of this element is LE. The coordinate of the first node is x1, y1, and the coordinate of second node is x2, y2. So my horizontal distance from node 1 to node 2, I will be taking the difference between x2 minus x1, and my vertical difference will be y2 minus y1. Now if theta, now we can see this element with reference to this x-axis, it is inclined at a particular angle. Let's take this as theta now here. Now considering cos theta, L is equal to cos theta, it's nothing but we know that adjacent by hypotenuse. We will be having this formula. Next, similarly for direction cosine of M is equal to sin theta, there's nothing but opposite by hypotenuse. We will be having this formula. Opposite to this angle is y2 minus y1, again the length of the element. Now in case of this the bar element in the bar element, since the truss element is equivalent to the bar element in the local coordinate, we have the stiffness matrix, this formula. And also we know that the strain energy in the local coordinate is having, we will be using this formula now here. Now we have defined the q prime is equal to L into q. Now substituting this q prime value in this one, we will be having this formula. Rearranging this formula, I will be getting this final formula here. Now comparing this formula with this one, I will be having the k dash, the k, this is equal to L transpose k prime into L. Now this L is nothing but the transformation matrix here. I will, if you want to have the transpose, you will be converting rows into column and column into rows here. Now next is, what we do is, we will be multiplying all these three things. That is nothing but transformation, transpose of the transformation matrix and this stiffness matrix in the local coordinate. Now multiplying all this, we will be getting a product, this one. Now this is my stiffness matrix of the truss element in the global coordinate. You have to remember this one. Now how to remember this one? L square, M square, L square, M square. It happens like this, and the upper part of the principal diagonal element, you will be having LM, LM, again the LM. Now similarly again you start with L square, M square, again you start with LM. Now the elements below the local coordinate, the principal diagonal, also repeat the same elements here. And you have to remember here, these 4 elements on the upper right column will be having negative signs, and these 4 elements on the below the principal diagonal elements, it will also be having negative here. Now remember this is the formula to remember this stress in the element. This is the main formula. Make a note down of this one. Similarly we will be remembering the equilibrium equation is k into q equals F. The same thing here, and also the reaction force, the formula. Let's start with the basic problem here. We have this problem in which we have 2 elements here, 1 and 2. The first element, the initial node is 2 and the final node is 1. And for the second element, the initial node is 3, again the final node is 1. We will be making this one. Now what they have given, for the 2 bar stress shown in the figure, determine the nodal displacement and forces. Now what have they have given? We have these 2 nodes fixed here, and this particular node they have given a roller support, and also there is a force acting 1 kilonewton. And because of this force, this particular node in the x direction, it can have a displacement of 50 mm. This is the given data. Starting one, I will be writing something called as nodal coordinate data. I will be taking node number x, y. Now there are 3 nodes here, first node, second node, third node. I will be writing those 3 nodes here, and after writing the 3 nodes, I will be writing the coordinates here. Now this is my first node here. I will be taking the leftmost node as the reference in each and every problem. Okay, from here to here the distance is 4 meter. I will be writing this one. Now from this reference, what will be the y distance? These both are collinear, hence I will be taking 0. Now similarly for second and third, try out this one. Now element connectivity data is my second step. I will be having this columns here. Elements are element number, initial node of that particular element, final node, length of those elements, direction cosines L and M. Now for my first element, the initial node is 2 and the final node is 1. Now I will be writing this initial node 2, final node 1, and I will be finding the length of the element by using this formula, root of x final minus x initial the whole square plus y final minus y initial the whole square. Now I will be telling this how. For the first element, I'll be considering these two particular nodes here. Now this is my final and this is my initial. X2 minus x1 the whole square. I'll be substituting 4 minus 0 the whole square plus y2 minus y2 minus y3 y2 minus y1 the whole square, that is nothing but 3 square. 4 square plus 3 square, I'll be getting 25, and root I'll be getting 5, hence this is the length of the element. Now direction quotient L and M you can find out by using this particular formulas. Try with the help of the calculator. The next step is finding the global stiffness matrix. It is comprised of element 1, element 2. Substitute the values, and each node will be having two displacements here. So each element will be having, since each element is having two nodes, each element will be having two displacement at each nodes here. So 4 displacement for each element, hence you will be having 4 cross 4 element matrix for element 1 and element 2. Now combining these two, you will be getting the global stiffness matrix. Check whether you people are getting this answer now. The force vector F is equal to, there are 6 nodes, hence we should have 6 force members here, and the force is being applied at the first node, hence I have written F1 is equal to 1000, and all the other nodes force acting are 0. Now my equilibrium equation is K into Q equals F. I will be writing the equilibrium equation. Boundary condition is here. We will be going back to the diagram again. Boundary condition is the nodes here, nothing but, now in truss element each node will be having two displacement. Now if I consider this first node here, this is my along the x direction one displacement, and along the y direction one more displacement, that is nothing but x displacement, y displacement. Similar at this node, x displacement, y displacement, x displacement, y displacement. So what I will be doing is I will be taking this as q1, q2, q1 along x direction, q2 along y direction. Similarly my second node, q3 along x direction, q4. Similarly here q5, q6. Now taking all these things and considering, I will be having, there are two nodes which are fixed. So at each node there are 2 degrees of freedom, hence I will be having 4 displacements equal to 0 for the element 1 and element 2. And q2, it is given as, q2 is nothing but the displacement along the x direction because of the force, it is 50. That is nothing but along x direction. So all the elements which are 0, I will be deleting each respective third column, third row, fourth column, fourth row, similarly up to sixth column, sixth row. Now finding out the q1, I will be having this answer. I will be rewriting this displacement matrix. Now to find the reaction force, R is equal to kq minus F. Rewrite all these things, find out the reaction. This is my reaction element. So check out this one. If you have any doubts, we will be discussing in the next classes. Now check this one. I will be sending you this file. Go through this one. If you have any doubts, kindly let me know. Thank you.